Hello, children. My name is and I would like to talk to you today about a fundamental force that is very dear to my heart. Fundamental force, of course, being a rule of the universe that sort of allows two things to affect each other without really touching. Now, you've all heard of such wonderful forces like gravity does that, and magnetism, which would do that if this was metal. But there's one that I feel that gets really overlooked all the time, and that is the strong like bull force. Now, you see, the reason you might think, well, hold on there, well, you don't, if it's so strong, if it's 1,000,000 times stronger than gravity, as it is even more stronger than that, then how come I've never heard of it? Well, that is because you've only operates at extremely short ranges, but at those short ranges it's stronger than anything else, so it only affects our lives in a very specific, yet if you think about it, very universal way. Like, this scale is so small, you look in this microscope, it's like nothing, you can't see it at all. In fact, it is a subatomic force, and it affects these things called quarks. Now, if you take this proton, which I happen to have here, and you empty it out, you'll see, as the poem 3 quarks for Muster Mark in Finnegan's Wake would entail, there are indeed 3 quarks in the hadron, as to so to speak. There's these up quarks, which are very upstanding citizens. They're very upbeat about their situation, and so they have these U-shaped smiles. Because they have very positive attitudes. But this down quark has a very negative attitude. And so you see he's sticking his tongue out, he's very angry. And his tongue looks like a sideways D, because a normal facing D doesn't look like anything. And so these are our quarks, and this is what color force affects. Now, I'd like to take a brief interlude here to talk about magnetism. Now, with magnetism, you have these 2 charges. See, one's positive and one's negative. They attract each other because they have 2 charges. Well, and in fact, the way they do this is with an interstitial particle called a photon, which you may have heard of it, as it makes up light. And so it goes from the negative to the positive. This is positive now. This becomes negative, and it sends it back and forth, kind of like if you've ever played a game of sports. Color force works similarly, except it has 3, which is why it's called color force. So it has red, green, and blue. But of course you may be saying, well, I was with you so far, but it is as if you are not aware that the Heisenberg uncertainty principle means that these things are too small to interact with light in the normal way, and therefore literally invisible. So how can there be colors if there's no light? Well, that's a good question. It's a good question, Jimmy. And the reason is because, well, there's no reason at all. It's just because at one point someone came up with a name for these 3 so-called charges, and the name stuck. So the force between these in strong like bull interaction is often called color force C, or just color force if you're boring. Color force works in a very similar way, except it uses this much more interesting particle called the gluon. The gluon is called the gluon because it glues quarks together. these quantum physicists are very literally minded. Well, the photon has no intrinsic charge. It just carries energy from the negative charge to the positive charge. But the way that color force works is these quarks are constantly changing each other's colors. So this one might turn to blue, and then this one turns to red, and then this one turns to green, and then this one turns to green too, and then blue and red, and so on. A quark has to actually send out a thing that carries color in of itself. So it has to carry a color and an anti-color. And what an anti-color is it basically just undoes this other color. So for instance, you have a red quark, right? And then you also have you have a red gluon, and then you also have a cyan gluon, and they come at each other, and they annihilate and make no color at all, which is in fact related to antimatter, where of course you have these anti-quarks. Look how angry this anti-quark is. He hates the normal quarks and their way of life, and so he desires to annihilate them. And so they go at it, and then, oh no, they annihilate each other and turn into energy. And so that's actually what happens, is that matter has one set of colors, and then antimatter has another set. So the way this plays out inside of a hadron is you have your, let's say this blue quark wanted to turn this green quark blue as well. Well, it would send out a gluon that's two different colors. It would send a blue color, as well as an anti-green, which is yellow color, and it would send these, and it would and then it would the anti-green would make the quark colorless, and then the blue would turn it blue. Of course, color force does a lot of other things, and it actually is what's responsible for holding together hadrons in an atomic nucleus. Yes. So how that works is, unlike other forces, color force is so strong like bull that instead of getting weaker with distance, it actually gets stronger. Now, the reason why this happens, and in fact the reason why it can't affect things across the universe, is because of a peculiar phenomenon called color confinement. Now, what this is if you imagine a color force field like an elastic band, right? You get two quarks that are held together by this elastic band. You try pulling them apart at a short distance. It doesn't let you. Try pulling them apart at a longer distance. Oh, it really snaps back. You see, it gets stronger over distance. But the thing is, if you put enough energy in, you just keep pulling and 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 pulling. The bond breaks. And so when that happens, an enormous amount of energy is released, and it sends off a quark anti-quark pair. Yes, and that a quark anti-quark pair, they would annihilate each other, but they've sort of just unannihilated, and now they shoot off somewhere, and they go and just hit another hadron, and that is in fact how hadrons are able to interact with each other using color force, even though they themselves have no color. So that's pretty cool. And of course, you know, the creation of quarks and anti-quarks is a fairly simple matter because, as we know, E equals mc squared, and when that's taken literally, it means that energy can be just turned into matter when there's a sufficient amount of energy. And since quarks don't have a lot of mass, that's actually fairly easy to do. This has been my presentation, and thank you for listening.